think the guys will see me like this. Okay, well, welcome. I can prepare this time. I have better markers. So quick note. I actually printed out the wrong document. So I updated the lecture slides, the order of it. The content is still the same, but the order of it will be slightly different. And the reason for that is I was actually going through it, and I was not very satisfied by the order, how it flowed. So what I did is I just updated that accordingly. So I will upload the, say, updated lecture slides as well. Let me again see how far I can go to the left. It's still there. Okay, good. So for today's lecture, we're going to focus again a bit more on stresses and strains. And the idea is for the lecture series on stress and strains, first re-examine basically what stress and strains are. Second, we're going to do the compatibility equations for strains, how you basically get those. And third, we're going to simplifications and how to solve a 2D problem. So basically that will be the topics discussed, and it might take 1 or 2 lectures or maybe a slightly bit more. So regarding stress and strains, the idea for stress and strain comes from the fact that, say if you have any specimen and you want to know something about when it fails. So in early days they figured out like, well, if I apply a force to it at a certain point it fails. So I get a an ultimate. So that's my failure load. And if I have material 1 and I change the geometry of it, then suddenly my say 1, FE1, and FE2, even though they're the same material, they're not equal. Okay. So the idea came from, okay, well, maybe geometry just plays a role. So that was the first observation. So geometry plays a role. And the second thing that we noticed, like if I keep the same geometry and I change to steel, then Fe3 is also not equal to Fe1. So there must be something that we can come up with, that we can at least take this part out of it, so geometry out of it, and then come up with a definition for a property that basically tells us a bit more about this differences between materials. So at first they said, okay, well, let's look at a cuboid from our specimen. So if we look at it, we have an applied force on it. And if we basically look at a small cuboid on it, then of course there will be a force on this as well. So in this case we have a uniaxial force, so probably we'll get some force here. But in this case we can have multiple forces acting on it, etc. So of course then we can also have multiple forces acting on this specimen. And they said, okay, well, if we know that geometry plays a role, let's see if we do basically normalize with respect to geometry and we get out of it. So they noticed, like, okay, if I take the force in x, just add a coordinate system to it. Okay, let's make this x, y, and z. Right-hand rule. If I look at the force here on fx, and I will see fy and fx. If I look at the force, I'm basically normalizing with respect to my area, which is x. So this is like a small incremental area. Then I can get my corresponding intensity, what we call sigma x, in this case stress x. So that will be your fx, your delta fx over that small area over the small area A. And then of course we can take the limit as we can say, well, let's take this as delta A goes to 0. Limit delta A goes to 0. and that's our formal definition of our sigma and stresses. So if we take the force in x, we get our stress in x. If we take the force in y, we get the stress in x and y, etc. So we also notice that we can have some shear forces that basically act on the surface. That let me see. This will be, say, let's get shear. Oh, let's call it still F, and this will be F YZ, and that reacts on the surface face, basically XZ. So if that area goes to 0, we can do the same thing for delta YZ goes to 0 with respect to delta A. In this case, delta A is the surface X upon, so it's not the same. It doesn't have to be the same A. And I take the limit again. This is what we call, again, still stress, and in this case would be YZ. And what we do in convention style is, for the direct stresses, that's your X, Y, and Z forces in the direction of X, Y, and Z, we use sigma, and for the shear forces, we use the abbreviation, the Greek letter tau. In literature, you will see in many cases that you can just use X, Y, and Z, and X, Y, X, Z, and Y, Z. So just whatever sign convention people like to do, okay? But they're basically the same. So this is the same. Okay. And another thing that I want to go in before we actually start with our main topics is how to come up with these different sub indexes mean. So so if we have, for example, let's draw a slightly better one. We have our cuboid again. And let's look at this one. Let's see, X, Y, and Z. So with this shear force, that will be known as tau YZ. And why is this not tau ZY or something else? So the convention is the first subscript indicates the outward normal. So if you look at this plane where it's x upon, this is basically acting upon on the xz plane, and the direction normal, the normal direction to it, the outward normal, is in line with the y-axis. And then the second subscript indicates the direction of the flow of the shear flow of the stresses. So that's the resultant normal, and this is the outward normal. So that's where it comes from. So in this coordinate system, say for example, if someone would give you tau yz is equal to 7. This would be positive. And if the same person would give it tau yz pointing drawn in this direction, going downward, then this value, even though the calculation value should be -7. And how you can know again whether it's positive or negative, we can basically use the same principle. What we can do is we take tau yz, we say, first of all, we take the magnitude of tau, that in this case is 7. Then we multiply it by the two normal directions. So multiply by, so tau yz in this case is this pointing normal to the surface of y. In this case, yes. So we multiply by direction y. We call this direction y, and then we multiply by direction z. In this case, y is +1. And in this case, the directionality is pointing downwards, while z is positive upwards. So this is -1. So therefore, you know that value for tau yz in this configuration is -7 or negative whatever number it is. So, of course, when we go back to our basically our rod or our cuboid, and we pull this, we said we can put a F force on it, we get some certain stresses, and what we can see from experimental phases, yes, we do get some stresses, but we also get is some deformation. So in this case, slightly longer than our original one, and the width will be slightly contracted. So even if we put the force on it, we get stresses, but we also get some displacement. So let's have a look at the second, say, property when we put something under a given force. So and that property is basically displacement and change of length. So what we get is displacement change of length. Okay. So we can also say something about that. So as we did for with our force, where we said, okay, we take the limit, we define a new term with what we call stress, and we can hopefully say something about that. Let's take that as well. So we're going to take a smaller, bit easier example in this case. We can just take a rod on the side, so 2D force. So this is Y, this is X. And we define a couple of parameters. This is the length L, the height H, and after deformation, what we get is a new form. So what we get is we have some additional displacement in X direction, displacement X, and we get an additional displacement in Y. So again, with convention, notation, etc. Once we have a displacement in X, we use the letter U for that. And once we have displacement in Y, we use the letter V for it. And X, Y, Z, U, V, W. So displacement in Z is W. Also, something is to note, noteworthy to mention. We use a coordinate system X, Y. This can be X1, X2, and then of course, then everything. It doesn't matter if you use U1, U2, U3. Just take it into account. During this lecture series, I'll probably use majority of the convention, which problem I took from a book. If they go in X1, X2, XZ, X1, 2, and 3, I will remain in that coordinate system. If they use X, Y, Z, I will do that. If they go VW, U, V, W, we use that. So just keep in mind that they're basically the same thing. They are the same thing, just different notations. So what can we see about, say, let's say if we had a force in X, okay? And we have a displacement in X. So what do we get? So if we look at the change in length, we know that, so we look at U. So now we have basically, so we get the change of length is basically the additional change of length is the additional length divided by the original size, basically percentage of increase. So we do that, so we do U over L, we get a change in length in that certain direction. In this case, in direction X. We can do the same thing for the direction in Y, and we get the change in length as B over H over 2 in this case, and if we add in W, then we get the same thing. If, say, for example, we had this as square, then it basically went from the larger square to the smallest square, then we get a change that's given by, this is W, and this is B, we get by W over B over 2. So that's basically how we define the change in length. And that's basically the correct term for that is strain. And basically, since we're dividing length over length, so meters over meters, we know that this is dimensionless. So going back to stresses, by the way, we said stress is force over basically delta F over delta A. That's called force over area. So in this case, we have force is given in newtons, area is given in meters squared. So that's Newton per meter squared, or also Pascal. So in this case, in the strain case, we have a dimensionless unit. And we can rewrite this a bit differently. What we can say is, okay, well, if we have a differential element, then the change in length is a differential of du, and the original length is increasing with delta x. So we can say, well, the strain is actually mathematically defined as du dx, dy dv y, and w dz. And it's actually not d, it's partial u, partial x, partial v, partial y, and partial w, partial z. Okay, so that's given us the strains based on the forces in the one direction or the displacement in the corresponding direction, x, y, and z. But again, as we had besides direct stresses, we had also shear stresses. Let's see what those corresponding counterparts with strains are. In this case, similar principle. We have a shear strain, and in this case, we denote that with the letter gamma. And for the shear strain is, we have to look at a slightly different picture to define what shear strain is. We have again our x and y axis. We have our regular plate or specimen. And what we do is basically put a shear force on it. So it basically changes shape in both, say, x and y direction. And if we do that, what we get is what we notice is that the lengths basically remain the same, but the shape is changed. And this angle here is a measurement of how much that shear strain is. So in this case, this is gamma xy. So again, we can define a certain parameter, in this case delta v, and in this case, this change in length or coordinate transformation, delta x. So we can say that the gamma, the shear strain x and y, is equal to the change in u, this is u, over the original length y, plus the change in v over the original length x. And of course, we go again within mathematical notation and derivative approach. Then we say this is du of partial u, partial y, plus partial v, partial x. So those are the terms, basically the shear stresses and the normal direct strain. We discussed normal stresses, shear stresses, normal strains, and shear strains.
So should it not be like delta u over x plus delta v over y? Because that's the if you're adding strain rates, is it the strain rates that you're adding, or is it something else?
We're looking at the change of angle with respect to x, y, and x. So you basically have to look at basically how this angle changes, because the length of itself remains the same. So if you use Pythagoras theorem, then you basically get x, and this is your
Oh, I got it.
delta
I got
b. Okay. Let's raise this a bit, and let's just see what we so far have determined. And it's basically just notation of stresses and strains. So we said stresses, direct stresses are Fx over A. And then we said, okay, well, of course, then we also have shear, and the shear, say xy, is basically xy over A, etc. And then for strain, we had a bit more, and the same is valid for x, y, and z. And the shear stresses, zx, xz, and yz. And for the strains, we had du dx. I'm going to write these out because we're going to use this later as well. dy, and then we have our shear strains, xy. That's du dy plus dv dx, yz, xc, I mean, and that's du dz plus dw dx. And then we have the last one, is yz, that's dv dz plus dw dy. And let me see. So we're almost there. So the strains, for the stress was quite direct, was simple, basically a one-way street. We have forces next, we divide that by the area taxa, get our stresses next. Same for y, same for z. For the shear force over the shear force area, we get our shear stresses. Very simple. One more notation, by the way. Again, just convention. You will see a couple of notations like sigma xx and epsilon xx. Basically, when we have a double repeating subscripts, we tend to just ignore the second subscript. So if you'll be 100% correct, this should be sigma yy, or epsilon xx, epsilon yy, epsilon cc, and then also for sigma xx, by the way, cc. So, but since we're all lazy, we basically ignore those. And that's only valid for when it's direct stress or direct strain. Because you cannot change this one, because then information is lost about how it acts and what it acts upon. So what do we get from this one, from this set of strain equations? So we can see that the strains are basically a function of displacements. So some displacements, and to be correctly, displacements are x, x, y, z. And so our location of u1, our location of u, our displacement u, that can be a function of our coordinates x, y, and z. And our b can be a function of our coordinates x, y, and z. This is u, v, w. And w is a function of our coordinates x, y, and z. We have basically, if we look at it, we have 6 equations. We have 3 unknowns, basically. So basically, And the problem is that we can come up with solutions that are basically trivial solutions. So in order to have a solution that works, that basically maps the correct strain field with the correct displacement field, we need to come up with some certain compatibility equations that basically you can test your function at to see if that's actually the correct solution to our problem. So the fact that we have basically 6 partial differential equations, these, and 3 unknowns, results in the need for some compatibility equations. Okay. So now the goal is, okay, how do we get those compatibility equations? So one approach is, what we do is, we go with the strains, sigma x for example, or epsilon x, and we take the derivative with x, y, and z. So x, y, and z, and that's basically all the variables that we have here. And the problem for this approach is we still don't solve our solutions. So basically, we will still get more equations than unknowns. Okay. So clearly, this approach doesn't work. So approach number 2, and I can actually show that if you take the derivative with respect to x, you basically get, again, too many equations and not enough unknowns to basically solve it and to have a non-trivial solution. It's basically 2 pages, so we're going to ignore that. So what we do for approach number 2 is we say, okay, well, let's take it one step further. We take the derivative with this second order derivative. So that means we take for sigma x with derivative with x squared, y squared, z squared, xy, yz, and zx. And to be fully correct, we also have to say, well, we're going to take it with yx, zy, and xz. But these derivatives, the order of the differentiation doesn't matter. So basically, the second pair is the same as the first pair. Okay, so we can ignore those. So if you take one of those, I really wish I'd print out the correct one. Now I have to do it by heart. See if I can remember this. So let's do that for basically this. So we take the partial derivative with the second order of x, and we take it with all the different derivatives. So x squared, y squared, z squared, partial x, y, partial x, partial y, partial, let's get correct notations, x, z, partial x, partial z, and partial y, partial z. And we can write this slightly differently. We say this is du dx. Basically, I just rewrote this as, let me see, yeah, I'm still not on board. So I rewrote x is du dx to, and this du dx is equal to 0. That's what I did. So you can do this. Basically, what you will get is 6 equations, because this is 1 equation, this is 2, this is 3, 4, 5, 6. So this gives us 6 equations. And we can basically repeat that for second order of this with y, partial b, partial y, and that gives us another 6. And we can do that all the way for all the 6 equations. So basically we'll have over at the end is 36 equations. So we can now examine basically what those 36 equations, how many unknowns we get out of those. Again, let's just take 1 or 2 examples. So we ignore all the rest. So if we look at this, and we take the partial derivative with x squared, what we get is and then we can do that for y, for z, for xy. For example, let's do it for xy as well. And we get etc. So basically get, let me see, 6 equations, and we can repeat that for the rest. And what we'll notice when we write everything out is that we have a couple of third order terms. Let's call that, third order terms, certain values. And we'll have some second order terms, like these ones. So it doesn't matter what's in it. So this third order terms basically will give us 30 equations, and this will be 6 equations. Yes?
Why does the notation of what order it is change from after the x to right after the delta?
How do you mean?
Like in the first line, it's
Yes.
partial x to the second,
Yeah.
and then it's partials to the second x in the second line, in the bottom.
Oh, no. There's again notation. It means it's exactly the same. It's again, I did actually incorrect here. When we're dealing with x, y, and z, and we're dealing with partials in mathematics, it's very common to write the partial, and then when you have x, y, and z, write x squared, y squared, etc. When you're dealing with, say, something like this, which is basically can be a function of u, x, y, its commonality is to note the partial, taking the second order derivative, and putting the square over the second order. As simple as convention.
I was just curious if it mattered.
Yeah, it doesn't matter.
Okay.
You will notice, like you just noticed, I'll probably intermix them all together.
Okay.
It doesn't matter. It's very common. It's normal to do when it's dealing with x, y, and z's to use basically put a square at the x, y, and z's, and then when it's say other variables, put it on the partial. But other than that, it doesn't matter. Again, also the order of differentiation doesn't matter either. Okay. So what we notice if we write everything out, and of course all the other terms as well, then these 30 unknowns, third order partial differential equations, will basically drop out. They can be eliminated. Now you have 6 equations that basically form what we wanted. We went basically from 6 equations, and those 6 equations that we left over are basically combinations of our sigma epsilon x's and the strains in x, y, and z, and our shear strains and our combinations of u and v. So basically, the remainder of these second order derivatives gives us what we needed, gives us our solution. And I will do 1 or 2 examples how Maxim does it. But this is basically the approach. The approach is not discussed in Maxim. I want to give you the approach, how they basically started it. And it was as simple as, okay, let's take it with x, y, and z, because we have here variables x, y, and z. Let's try that. see if it works. It didn't work. Okay, let's try our second order derivatives. If that didn't work, they probably would go to the third order. If that doesn't work and fourth doesn't work, then you see, okay, well, then my approach has to change. But in this case, the second order worked. It will give us six equations that we can actually use. That together with our six strain equations gives us a condition that must be satisfied in order for our solution to be a non-trivial solution. So now you know at least where it comes from. I think in Maxon he just jumps into it. He says, okay, let's take the partial derivatives with x, with y. Let's combine a couple of these terms together, and bam, you get your compatibility equation. But this is the approach that was basically used. Cool. It continues recording. Yes, perfect. Yeah. So let's look at one of those examples we do, basically how Maxon does it. Again, just keep in mind that what we do is we just take the second order derivative, and the reason why we take the second order is because actually if you work it out, it works out. So this is not something out of the blue, which if you read Maxon, it comes a bit of out of the blue. It doesn't give you a very good explanation why the second order is taken. So Maxon, he looks at the shear strain. Shear strain. It says we have this as u dy plus dv dx. And you take the second order derivative, in this case, with respect to x and y. And if you do that, okay, second order derivative with x and y, and u dy, plus the second dx. And then we can collect terms. We can basically, we have two double dy's here, so we can take this and then use du dx. So we get it dx plus dv dy. And from here, we know that this is nothing else than your direct strain in x, and this is your direct strain in y. So we can rewrite that again. And then we can repeat that for the other shear strains. And then what we get is, if we do the complete set, let's just rewrite this again. plus 1. Let me see which one am I missing?
YZ.
YZ. Partial Y, partial Z. Y squared Z. And this is basically our first 3 compatibility equations that we have. Basically, like I said before, if you would do the whole 36, and then you can see you can eliminate 30 out of them, 6 remain. These are the first 3 of those 6. Okay, and they start off basically by taking your shear stress, shear strains, and taking the second order derivative, and these are the ones to remain. And this is the reason why I said like the approach in Maxen, you basically start off with this. It's like, let's assume this, we take the derivative with x and y, and bam, this is our equation. Not telling you where it comes from. So there's a bit more background information to it. And we can do the same for basically the other set of equations that remain, basically come from taking the second order derivative, and again of x, the shear strain, xy, with respect to partial x, partial z in this case, and adding that with another partial derivative of gamma xz, and taking those derivatives with respect to dx dy. And then if you do that, you can reuse some of the notations here. We'll see that we have dx dz. We plug in our shear strain, so we get du dy plus dv dx plus partial derivative with dx dy, and then this was xz. Xz is partial u partial z plus partial w partial x. And then again, we do some just shifting around. What we can do is, we see we have a partial x here, so let's take that out. So we get a partial derivative with x, gamma xy over c, partial u plus partial gamma xc over y. And here, again, we can do the same. We can expand it and then collect the terms. And if you do that, you get partial second order partial derivative with y with z of du dx, or partially partial x, plus partial order, second order derivative with x squared of partial b with respect to z and partial w with respect to y, plus second order derivative with partial y, partial z, and this is du dx as well. And then we can again collect a bit more terms. We can write this as sigma x. We can take it to the other side. We have a 2 here because this is the same. So we get is 2 times partial y partial z of sigma of epsilon x is equal to, so we know that all of these have partial x involved with it, so we can take that out of the bracket, and we can rewrite this as gamma yz. So then, taking everything to the other side, what we get is minus gamma yz partial x plus there's a partial sign here as well. Xz with respect y plus partial gamma yz. Let's say this correctly. No, yz I already had that, so I'm looking at xy, sorry, with z. And this is our second compatibility equation. And of course you can have all 6 of them, but instead of that I'll just go to the lecture slides because I really don't want to write it down. Oh, am I on the way, by the way? I hope you can see it. I'll pop it up in the lecture slides so you can see it a bit better. Okay.
These lecture slides will be posted?
Yes, they will be posted. I will upload them to later today. So let me see. It's 12:55 the lecture, right? We have 20 minutes. Okay. Let's do a quick refresher and then we can hopefully do the stress-strain relationship. Like I said, I reshifted a bit around. I should have talked about stress-strain before going into this, but we can do that very quickly. It's not that difficult. So let's do a refresh from today's lecture. So just following the lecture slides, and then I think it's a good location to stop for today's lecture, and then we will continue next week. So like I said again, start off with basically taking forces, looking at how failure occurred, and for that is taking an arbitrary shape, putting a force on it, noticing that the forces are basically also internal forces, and then if we want to have, say, something that is basically geometrically independent, we could basically normalize with respect to the area that yielded intensity that we call stresses. And of course, taking the stress at direction x gives you sigma. The force in direction x gives you stress in direction x, and xy and xy, blah blah. So that's basically the first couple of slides. Then we went into refreshing the strains, how basically are calculating our strains, and direct strains in x, y, and z. Basically, function of our change in length in u with respect to x, and v with respect to y, and w with respect to z. For the shear strain, we noticed that good observation was made back in the day is that yes, you change the shape, but the shape sizes do not elongate. So there's no change in length, but just in shear, basically the shape changes, and that's the shear angle, also known. So for the 3D forces, when we have like all the directions, basically have x, y, and z's, and our shear strains in xy, xz, and yz. We discussed a bit of the sub-indexes or subscripts. To determine that, again, we take this magnitude, we multiply with a positive, -1 or 1, depending if it's in a positive direction or negative direction. And based on that, we continue. So this one thing I skipped. So the next idea back in the day when they start off with these directs, when they got their, when they found their stresses and they saw that, okay, well, we also have some displacements to worry about. They still wanted to have something. They're wondering, well, if I double my force or double my stress, what happens to my strain? And they figure out, Luke's law comes from that. They basically figure out that actually the forces are proportional to the displacements. So forces here, displacements here. They're proportional with some given constant k. This also still, in this case, the constant is just a given arbitrary constant. So they noticed when they looked at actually, well, we know that forces were basically proportional to stresses. So basically say, well, if this proportionality is valid, then this proportionality must be valid as well. And based on experiments, they noticed like if you do it actually for multiple stresses, there's multiple strains, you measure those two, there will be a linear behavior, and this slope, that's what we call our Young's modulus E. So that's our proportionality constant. And this is valid for metals. So for isotropic material. So what do I mean with isotropic material is basically if I have my cuboid, if I would pull it in x direction, it will displace the same as if I would pull it in the y direction, only in the y direction, or only in the z direction or in the x direction. Let's go back to our lecture slides. And that's where it comes from. So they notice like, okay, well, of course, if we take the inverse, we can take the inverse, we can say 1 over E sigma. For composite materials, this is a bit more complex. It's not as straightforward. And the reason is basically composite materials nothing more than a bunch of carbon fibers orientated in a certain direction. If you look at it as a carbon fiber, just like rope, if you pull on it, it's very strong. But if you try to pull it in the transverse direction, in the two directions, it's weak. And if you compress it, it's also weak. So for composites, there's not one constant. Basically, you have a constant in X, you have a constant in Y, constant in Z, etc. And this is basically better known as our stiffness matrix. That's given with the letter C. So confusing, but again convention. C is our stiffness matrix. And S is our compliance matrix. Okay. No idea why they did not flip it around. So basically, if you take, yeah, this is incorrect. This should be like this. So basically, yeah, C is the inverse of S1, and this is basically 6 by 6 matrix. And depending on how anisotropic the material is, it can be all 36 components be filled in. The majority of the time, you will have a bunch of assumptions, or you have your shear components activated by the G modulus, and then you will have 1, 2, 3, 4, 5, 6. Probably you have 9. That's the most complex, often is used. So this will be your diagonal will be EX, EY, EZ, the shear strains, shear moduluses, X, Y, X, Z, and blah blah. And then you have some transverse components. Often the matrix is symmetric, so that simplifies it a bit. So going back to our material of isotropic material, just got a bit sidetracked. So we noticed, let's make it a bit simpler. We noticed if you have something and we pull it in the x direction, that basically our material elongates, but shrinks in the transverse direction. The ratio for that, again for that composite, so they noticed if I have my sigma x, that's my 1 over Young's modulus in x, stresses in x, and even though I only have a force in x and therefore no direct correlation between sigma and x in y direction, I will have some strain in y as well. And the strain in y came to the fact that if I elongate in one direction, I will shrink in the other direction. and that force was basically negative this ratio, which is known as the Poisson ratio, and for metallic is 0.33. For composites, again, determines on your 1, 2, or 3 direction, but they can range from 0.05 all the way to 0.4 something, or even higher. And there you can even engineer materials, structures like metamaterials, wherein the material has certain structure, where you basically pull in one direction and expands in the other direction as well. So you get a negative Poisson ratio. But everything for the course, we just use metals, so we can just assume 0.33. So, of course, we can expand this a bit. We can expand this effect saying, okay, well, if sigma y, if I only have a sigma epsilon x, but I get an epsilon y. If I have an epsilon y at the same time, then there will be contribution from, there will be interdependent, there will be a couple of coupling pins, and then we can basically come up with a generic form, which are generalized Hooke's law, as shown here. So in this case, our alpha, delta t, this is here just to have it complete. That's basically the expansion due to a thermal effect. So if you put in some material and then heat the chamber, it will expand. That expansion in all the directions is equal, so that will be an equal. And alpha is known as the coefficient of thermal expansion. So again, for Hooke's law for shear, there's also Hooke's law for shear. In this case, tau is equal to G times gamma, where the shear modulus for non-isotopic material is given as E over 2 plus 2 multiplied by 1 plus the Poisson ratio. We have no Poisson effect, no temperature effect, therefore the generalized Hooke's law is just given as is. They're much simpler. And this will be our complete set of equations. So we skipped that during the initial part of the lecture, so that's already a bit Hooke's law. Then we went into basically what we discussed earlier was, okay, let's collect all the terms. We have UWV, we have sigma x, we have 6 stresses, 6 strains. And if you look at the stresses, if I look at the displacement and the strains, we see that we have 6 partial differential equations, PDEs, we have 3 unknowns, so we have to have something that basically tells us if a solution is an algebraic solution or basically our solution that we satisfies our conditions. For that, we basically looked at the first approach. We take a derivative of the strain equation with respect to displacements, variables, that's x, y, and z. And we noticed that if you do that, you will not yield, you will still have more equations than unknowns. So another 10, there's notes shown here. So when taking derivatives, what I did is I used the partial signs, so partial epsilon x with partial x. This is one way to denote which variable you take the partial derivatives with. Another form is basically using a comma notation, and in this case that will be like this. So in this case the comma here, x, tells you you're taking a partial derivative with respect to a given variable. So it's x comma y z. This means basically the second order partial derivative of x, of strain x, with respect to partial y, partial z. Again, there's some notations that we probably will use. So if you see a comma, it means partial derivatives. I've shown it because I think in a book they use it once or twice. Most of the time I will stick to this notation. Okay, so like I said in the lecture as well, if you take approach 1, we basically still have too many equations for unknowns, so we don't know exactly if our solution will be accurate. So we went to our second approach. We basically take second order derivative with it. So we go with partial x squared, partial y squared, partial z squared, xy, yz, xz. And in this case, if we take all the second order partial differential equations for all the strains, both direct strains and shear strains, we get 6 equations for each, 36 equations total. Then we can look at the third order derivatives. Well, we have some third order derivatives and we have some second order derivatives. If we do the full extent of the equations, we know that our third order derivatives basically cancel out. We can eliminate them, remaining with 6 equations, which are our compatibility equations. So what this basically means is, if we have a solution field of x, y, and z for a given strain, these equations must be satisfied in order for our solution to be a valid solution. If they're not satisfied, then we have a problem. Then basically a solution does not work. Or your proposed displacement field does not yield the correct strains. Yes?
So just to clarify, with those 6 solutions, if we're testing one and we use, say, like the first equation, do we have to also validate the equation directly to the right of it? So like both have to be satisfied?
All have to be satisfied at the same time.
Okay.
Yeah, this is just condensing it into making sure they're available next to each other on the same slide.
Okay.
It's not like one line. You can choose to have one satisfied and not the other 5. This all 6 must be satisfied at the same time. We will notice that later on. I think next week or the next lecture, especially when it comes to aircraft structures, we're never dealing with a 3D problem. We can always make simplifications. We can reduce that to a 2D problem, and 99.99 times. So that reduces also the compatibility equation that we need to satisfy, because some of things can be set to 0. So, like I said, if you do all the 36 equations, you will see that 30 basically can be eliminated, 6 remain, and those 6 equations are compatibility equations. And we showcased one example that Maxon does. He starts with the strain in xy. You take the differentiate with respect to x and y, and then you basically rewrite that to get your first 3 set of equations, compatibility equations, and then the second set of 3 compatibility equations are taken by differentiating gamma xy and gamma xz with x and z and y and x and y respectively, and you add those together. That's one other way to get those. But this approach comes from this second approach I discussed here. They basically just taking all the derivatives, second order derivatives, and realizing that the 6 equations left are exactly what you need that satisfy our strains with respect to displacement variables x, y, and z. Good. I think that's a good location to stop. So for the next lecture, what we will do is pick it up from Maxon. What I actually did is, this will be, if you look at the book, I think there's more chapter 1.10. So I think there's a slightly better flow to it. Still not 100% satisfied, so the lecture slide might change again over the course of the lecture, but I will let you know. But next week, what we look at is the strain equilibrium equations and how we can go calculate stresses and how stresses transform based if it's in the x direction or at an angle, and we will introduce a methodology to solve a 2D stress problem. Okay, are there any questions? No? Okay, perfect. Thank you very much and see you next week.